Ladies, this is section 8.4. This is your video that corresponds to goal 1. We're taking a look at the binomial theorem. The binomial theorem is a theorem that allows us to raise a binomial expression to a power using patterns. I know that you can raise x plus 0, I know that you can raise x plus y to the 0 power with really no thought. You know any value raised to the 0 power is equal to 1. I know that you can raise x plus y to the first power, and that gives you the binomial x plus y. I know that you can easily square x plus y squared and x squared plus 2xy plus y squared. But can you raise a binomial to a power larger than 2 in an easy manner without having to write out x plus y 3 times and then distributing and multiplying and adding and subtracting like terms? Or if you did the same thing with this binomial to the 4th power, you would have to write that out 4 times and then take care of all the distributing and combining like terms. So the binomial theorem is a system in which we can expand a binomial using a set of patterns. I want you to take a moment and analyze each equation, both sides of the equation, and then all 6 or all 7 of the equations that I've already listed for you, and see if you notice any patterns at all. So I want you to pause this screencast, look for some patterns, and write them down over here. Let me quickly point out some patterns that I hope you noticed. Did you notice that the binomial raised to the 0 power contains 1 term? The binomial raised to the 1st power contains 2 terms. The expansion of the binomial raised to the 2nd power contains 3 terms. The binomial raised to the 3rd power has an expansion that contains 4 terms, and this continues. So one pattern I want you to recognize is that when you raise a binomial to a power, the expansion will always contain 1 more term than the power of expansion. So we could say that the number of terms is equal to the power of expansion plus 1. All right, so that's one observation. Let's see if you came up with another observation. I also notice that let's start with x plus y to the 6th. X plus y to the 6th is a binomial raised to the 6th power. The first term in the binomial is x. When I expand this, the first term in the expansion is x to the 6th. The second term contains x to the 5th, x to the 4th, x to the 3rd, x to the 2nd, x to the 1st, and finally x to the 0. The second term in the binomial is y. In the expansion, the first term is y to the 0, y to the 1st, y to the 2nd, y to the 3rd, y to the 4th, y to the 5th, and y to the 6th. So we can say that the first term in the expansion is raised to the power of expansion, then the degree decreases by 1 for each consecutive term. And then we could say the same thing for the second term in the expansion, but rather than the second term of the expansion, the second term in the expansion is raised to the 0 power. Then the degree increases by 1 for each consecutive term. So one starts with the power of expansion and the other ends with the power of expansion. Now that we've discovered this pattern, tell me what you notice about the degree of each individual term of x plus y to the 6th. The degree of term 1 is 6. The degree of term 2 is 5 plus 1, which is 6. The degree of term 3 is 6. The degree of term 4 is 6. And term 5 is 6. And term 6 is 6. And the degree of term 7 is 6. So another important pattern that we see is the power of expansion is the degree of each individual term of the expansion. I'd like to point out another observation that I hope you made. This observation has to do with the coefficients of each term in the expansion. If you notice, the first term in each expansion has a coefficient of 1, and that will always be true. The second term in the expansion, its coefficient matches the power of expansion. Second term here is plus 0. Power of 1, second term coefficient of 1. Power of 2, second term coefficient of 2. Power of 3, second term coefficient of 3, and so on. In addition to the first term having a coefficient of 1, the last term will also have a coefficient of 1. So the first and last terms of an expansion, of a binomial expansion, will have coefficients of 1. In addition to the second term having a coefficient that matches the power of expansion, the next to last term will have a coefficient that matches the power of expansion. For example, the power of expansion is 6. The second term and the next to last term have a coefficient of 6. When you have a power of 5, the second term in the expansion has a coefficient of 5, and the next to last term in the expansion has a coefficient of 5. When the power is 4, the second term coefficient of 4, and the next to last term coefficient of 4. So I hope that you have jotted down these patterns, and I hope you'll find them useful. I want you to try to expand x plus y raised to the 7th power, and I want you to use the patterns that we've discussed here. Now, I know that you will not be able to come up with all of the coefficients using the patterns that we've learned, but you should be able to come up with the first two and the last two. So for the coefficients that we have not discussed, just draw a little horizontal blank space, a little horizontal line, leaving a space for that. So please pause the screencast and use these patterns to expand x plus y to the 7th. Okay, let's see how you did. The power of expansion is 7, so the first term should be raised to the 7th power, then the 6th, the 5th, the 4th, the 3rd, the 2nd, the 1st, and x to the 0. The second term is y, and when we expand, we should have y to the 0, which is 1, y to the 1st, 2nd, 3rd, 4th, 5th, 6th, and y to the 7th. And then finally, our coefficients, we know that the first and the last coefficients are both 1, and the second and next to last coefficients are both the power of expansion, 7. So I hope you did pretty well expanding this. I now want to discuss how can we find these coefficients of expansion. So our first goal, now that we understand these patterns, is use the binomial theorem to calculate the binomial coefficients. The coefficients of binomial expansions have a special name. The coefficients of each term in a binomial expansion are called binomial coefficients. Really special, right? So binomial coefficients. To determine the coefficients of the binomial expansion, we use a part of the binomial theorem. This information here in yellow is the technical expansion using the binomial theorem. These are the patterns that we just discussed, and I don't want you to get caught up in that. I want you to get caught up in how do we find the coefficients. So the coefficient of each term, this represents our term, x to a power times y to a power. Well, the coefficients are given by this formula right here. And you would read this in combinations of r. And we would symbolize it using the symbol parentheses with n and an r inside of it. And this is, you can read this in above r. So to calculate the coefficients for binomial expansion, we use n above r, which is equivalent to this formula right here. Well, you know how to use formulas. We just have to be able to identify n and r. So let's look back up in this example. I see n right here. N is the power of expansion. So n is the power of expansion. R is the power that y is being raised to. Well, what's y? Y is the second term. So R is the power of term number 2. If we look back at our previous examples, let's look at x plus y to the 6th. N is 6. R starts with 0, and then it becomes 1, 2, 3, 4, 5, 6. So R is 0, 1, 2, 3, 4, 5, and 6. And x plus y to the 5th, R is 5. And N is 5, and R is 0, 1, 2, 3, 4, 5. And x plus y to the 2nd, N is 2, and R is 0, 1, 2. So you see that R changes from term to term. So R is dependent upon the term that we have. All right, so let's first begin by learning how to calculate these. So I know that N is 6 and R is 2. So I would have 6 combinations of 2. Or n factorial, so 6 factorial, divided by n minus r, or 6 minus 2, 4 factorial, times r factorial. Okay, so we know the shortcut to expanding. We would expand 6 times 5 times 4 factorial, divided by 4 factorial, times 2 times 1. We know the 4 factorials will cancel. 2 will cause the 6 to reduce to a 3, and that gives us 3 times 5 is 15. This is equivalent to 15. So the coefficient of the expansion with a raised to the 6th power and the term that contains y to the 2nd would have a coefficient of 15. Now, I know this takes a long time to calculate these by hand, so I want to show you how to calculate these using your calculator. So take your calculators out now. So I definitely want you to use your calculator to calculate n above r, so let me show you how to do that now. So you want to add a calculator, and to get this NCR on your screen, you would go to Menu, Probability, Combinations. Once you have that up there, you enter the value of n. So in this case, for number 1, that's 6, comma, the value of r. In that case, it's 2, and that gives you 15. For number 2, I would just go up and cut and paste and go in there and replace the first value with 3, comma, 0.